Good morning to everybody. So we continue discussing the properties of the Kashaev quantum logarithm function. So this is the last chapter of the course, which is called Teichmüller TQFT, which we started already last week. And I would like to remind you what we were doing in the end of the last lecture. So we were proving a theorem about the Fourier transformation formula for the Kashaev function. So recall the theorem on the Fourier transformation formula. For phi b of x. And the formula was, so there exists a z0 in C such that phi b tilde of z equal, which is defined by the integral of reals shifted upwards by quantity epsilon, phi b of u e minus 2 pi I u z du. And the formula reads as zeta 0 multiplied by minus pi I z squared phi b of cb minus z, where cb is defined by I over 2b plus b inverse. What else? Epsilon should be positive, but the imaginary part of z should be positive, but less than epsilon, and epsilon should be less than 1/2 b plus b inverse, which is the absolute value of cb. And so we started the proof last time, and we ended up at the formula. So in the proof, so we assumed that B inverse is bigger than B, right? That was a necessary condition to proceed with a functional equation, which is not big deal. The only case we were missing is when B equal B minus 1 equal 1. Any other case is contained in this condition. In the proof, we assumed and obtained the functional equation. Which was f of z minus ib over 2 equal minus e minus pi ib squared, f of z plus ib2. Where f of z was defined as a phi b tilde of z times what? times phi b z minus cb. That's the relation we ended up last time. And this can be written equivalently as f of z equal minus e minus pi I b squared f of z plus ib. And now we have to do something with this equation. So first of all, we want to remove the constant multiplicative factor. So what we do with it, so let us look what we can do. First of all, of course, taking into account the fact that phi b is symmetric under b minus 1. So we would like to keep this symmetry as much as possible on our treatment. So for example, f of z is still symmetric in bb inverse because everything, so phi b itself is symmetric, but cb is also symmetric in bb inverse. So we would like to have f of z as so the equation for f of z to have a symmetric formula for. So we have to do something with this coefficient, which is not symmetric in b inverse, something which would restore the symmetry. So that's what we do. So we write minus e minus pi I b, and I separate one b, and to the second b I add the inverse of b. What changes is that we add a sign here, because a minus pi I b inverse will be e2 minus pi I, which removes this minus. Okay? And then, so we can put here 2 and divide by 2, and we can absorb I. So this will be CB, symmetric object. And the minus we treat as a e squared. I squared, 2 pi I, CB, IB. That's how we rewrite this coefficient. And now look what we can do. Now we can rewrite this as follows. I multiply f of z by 2 pi I CB z. So just I multiply this equation by this exponential. And now I use, for this coefficient, this formula. And as you see, we write this as e2 pi I CB z plus IB, f of z plus IB. And now you see what happened. So we managed to absorb the multiplicative factor. If we denote this g of z, then this equation is equivalent to g of z equal to g of z plus IB. So it is IB periodic function. And now what remains to do is to prove that the g of z is constant function. So now it remains to prove that g of z is constant. Why? Because if we solve it, now recall our definitions of f and g, what we see that phi b tilde of z. So if we solve it, what is it, from the equation defining f, where was it? Here. So we have to divide f of z, divide by phi b z minus cb. And now we solve for f of z from the equation defining g of z here. So it is g of z e minus 2 pi I cb z divided by f of b z minus cb. And then I can multiply the numerator and denominator by phi of the negated argument here. And use the inversion relation in the denominator. So we finish g of z divided by phi b of 0 squared e minus pi I cb squared e minus pi I z squared phi b z minus cb minus z. And so if g of z is constant, then this combination is identified with zeta 0. Because we reproduce this formula. And to prove so the g equal of z is constant is a consequence of the Liouville theorem in complex analysis. Liouville theorem in complex analysis, and the following lemma. So what is a lemma? Today is the 12th lecture, first lemma. So g of z is a bounded analytic function in the strip. Imaginary part of z is bigger than 0, less than b plus b inverse half. Why this lemma implies, so first of all, the lemma implies that g of z is bounded on the whole complex plane because it satisfies this functional equation. So if it is bounded in the strip, which is wider than the value of b, then by the IB periodicity, it is bounded on the whole complex plane. And the only bounded analytic function on the whole complex plane by Liouville theorem is a constant function. So that what remains to do for us is to prove this lemma. Okay, so let us do this. Proof. Yeah, so we have two formulas for our function. Sorry. So let us write the formula again for g of z, because we are studying now the properties of g of z. So we solve it again with respect to g of z. So g of z equal e 2 pi I cb z phi b of z minus cb phi b tilde of z, right? That's one formula, but using the inversion relation, we have a second formula, which is a phi b 0 squared pi I CB squared minus pi I Z squared phi B of Z tilde divided by phi B of CB minus Z. So we have two equalities, and now, so it is clear that G of Z is analytic in our strip, because phi of Z is analytic, because we stay, remember that the imaginary part of Z is less than 1/2 B plus B inverse, and positive, so we are in this strip. Right? And here we have a point that CB, which is the first pole of the function phi B. And we have a further poles in the upper part of this line, but the very first pole, simple pole, starts here. You remember the structure of the poles? Poles of phi B of Z. So this IB times M plus 1/2 plus IB inverse N plus 1/2, where Mn are non-negative integers. And for M equal N equal 0, we have 1/2 IB plus 1/2 IB inverse, which is CB. So this is the very first pole. And then when we add, we add the imaginary quantities of strictly positive imaginary part. So we have a finite gap here from the rest of poles. Okay. So, but the very first pole finds here, and exactly through this point passes the boundary of that strip. And so. And so this formula tells us that, so you see, CB minus Z, the imaginary part of, so minus imaginary part of Z is bigger than minus 1 over B plus B inverse, less than 0. And when I add this quantity, 1/2 B plus B inverse is bigger than CB minus imaginary part of CB minus Z, right? Bigger than 0. So you see that this argument still finds itself in the strip where phi B function is analytic. So this is analytic by construction, right? We learned it from the Fourier integral, its convergence properties. This is analytic, so G of Z is analytic in this strip. That's the first thing. And now, what remains for us to show that it is bounded at infinities of that strip. If we manage to prove this, then we prove the boundedness of G of Z. And this is very easy to see when real part of Z goes to plus infinity. So G of Z goes to 0 if a real part of Z goes to plus infinity. Why it is so? Because when the real part of Z goes to plus infinity, the real part of the argument here goes to minus infinity. So this phi goes to 1 from the property of the function phi B. This goes to 1, and then this guy should go to 0. Does it go to 0? So let us see this exponential. So if we write z equal x plus iy, then e minus pi I z squared, right? This exponential factor, what is it? Its absolute value is given by e minus pi I. So we have to leave only the imaginary part of z squared. So it is twice xiy. Sorry, it's a plus, right? There was a mistake here. Otherwise, I will not arrive to a proof. Look here. So I'm using here the inversion relation, which contributes e to I pi square of z. And when I expand these are the square terms, and mixed term went away. So it's important to have plus here. And now look at here. So we have this, right? The imaginary for the imaginary part, and this is minus 2 pi I x y. And now this goes to 0 when x goes to plus infinity, because y is positive. Because y is the imaginary part of z. So this exponential goes to 0 when x goes to plus infinity. So this goes to 0, this goes to 1, and this is a Fourier image of Schwarzschild function, right? In the strip phi b so phi b tilde is a Schwarzschild function as a Fourier image of a Schwarzschild function, right? Our integral was converging exponentially at infinities, so phi tilde is rapidly decreasing when the real part of z goes to plus or minus infinity. That's clear just from the definition of phi tilde. Right, so phi tilde of x plus I y is in Schwarz class. Schwarz function. In here. Yes. No, because it is I squared gives minus 1. Thank you. So if y is positive, and less than 1/2 b plus b inverse, so that this condition is needed to stay the contour of Fourier integral to be here. And so we have this property of phi. So at any one of two infinities, phi tilde goes to 0. And we know that this goes to 0 at plus infinity. This stays bounded at plus x at plus infinity. This goes to 0. So we have this property. So no problem at plus infinity for g of z. The only problem is at minus infinity, because now this grows exponentially, this factor, which means that for g of z to be bounded, phi tilde should kill this growth by its decay. So it should decay more rapidly than this growth, or it should be exactly this. It should decay with the same rate of. But also there is a problem with the denominator, because when we should use this formula now. When the imaginary part of real part of z goes to minus infinity, this is bounded, that's okay, but this grows. And so the decay property of this phi tilde should remove this growing factor. And that's what we are going to see now. Now the behavior of at real part of z goes to minus infinity. Okay, so let us see what we can do. So the first thing we do is the following. So we write the phi tilde b of z as the integral of a contour c of phi b of z of u e minus 2 pi I u z du plus residue 2 pi I, the residue at u equal cb of the integrand. uz. Okay, where we have defined the contour in the u plane. So we have CB here. Somewhere here start the rest of the zero poles of phi b, and we put the contour C just above the first pole. Okay, at the height h. So the height h is bigger than 1/2 b plus b inverse, but not much. We put all other poles to the upper part of the path, and on the way, but before the Fourier integral, we had the contour going somewhere here, and now when we push the contours, we crossed one pole, and so we corrected our integral by adding this residue. Okay. So that's why we need this. And now let us calculate this. So what is this? This is equal 2 pi I residue, because the pole is contained in phi, not here. So this is a residue at u equals cb of phi b of u. And it suffices to specify z to cb in here. E minus 2 pi I cb u. And just now look at, let us see at this formula. So remember, this is bounded at when z goes to, when the real part of z goes to minus infinity. And now the contribution, the residue part of phi tilde is a constant. This is z independent part. Times, sorry, this is z, right? Because u was specified. Times the negative exponent of that. So it exactly cancels this growing term. And so this part, which enters into the expression for g, stays bounded. Right? And actually it stays constant. So the only thing which remains is this integral. So this I will call, okay, let me define. This is integral I of z. Right? The only thing which remains for us to see that the I of z behaves nicely to see that g of z is bounded. Okay, let us do that now. So I of z. So I of z, I write it as I plus of z plus I minus of z, where I plus minus of z equal integral over c plus minus phi b of u e minus 2 pi I u z du. And the c plus minus are just correspond to signs of the real part of the integration variable. So these are u belonging to c, such that real part of, let me put it this way. T plus IH, this is a height where t lives in plus minus t lives in R non-negative. Okay, so the left half of CB is called C minus, and the right part of C is called C plus. So we have split it, this integral into sum of two smaller integrals. And now we are going to estimate the absolute values of E plus and E minus. Now let us start from E minus of Z absolute value. So it is by integral triangular inequality. We have from integral from minus infinity to 0, phi b of t plus IH absolute value, E minus 2 pi I t plus IH times x plus IY. Right? The x plus IY is always the expression I'm using for Z. Absolute value. dt. So, first of all, t is negative. So this is bounded, because at infinity, at minus infinity, it goes to 1. It is continuous, so this is bounded. So this is less than m minus for some constant m minus. So we have to calculate this. So less than equal m minus integral from minus infinity to 0. So we have to take the real part of that. So we have to take imaginary part of this, right? E2 pi t times y plus h times x. Is that correct? I hope so. So this is t independent, so this goes outside, m minus e 2 pi hx. But the rest is easy to integrate. So we get the denominator 2 pi y. So exponential goes into. And now at minus infinity, remember y is positive. So at minus infinity is 0, at 0 it's 1. So that's the result of integration. And h is positive, and when x goes to minus infinity, this rapidly goes to infinity. And if you look at the growing exponential factor, 2 pi I cb z, right? The absolute value of this is e minus 2 pi b plus b inverse half x. And h is strictly bigger than this quantity. And so this is, goes stronger to 0 than this goes to infinity. Okay, by the choice of the h bar. So the consequence e minus of z multiplied by 2 pi I CB z goes to 0 when real part of z goes to minus infinity. Okay, we are safe now for I minus. Now I plus. I plus is the integral now from 0 to infinity. The absolute value less than or equal. Again the triangular inequality. So phi b of t plus IH, absolute value, and nothing changes, right? So we still have same exponential here, 2 pi t y plus hx dt. But this time now we have to use the inversion relation to put negative t in order to use the boundless property for phi. So this is equal integral from 0 to infinity. Okay, so let me pull out this constant e 2 pi x h. And the rest is integral from 0 to infinity, and 1 over phi b of minus t minus IH, absolute value. And what remains here, e absolute value of pi I of that argument, t plus IH squared, absolute value. And e 2 pi ty dt. Okay, so this part stays bounded because t goes to plus infinity, so the argument of phi goes to minus infinity, this goes to 1. So this is less than some m plus. So we can pull it away, and the rest we just calculate. So m plus less or equal m plus e 2 pi xh, and we have to take the real part of that, which will be e minus 2 pi t h minus y, right? Because this is 2 pi ty, so we have two minuses, and the contribution from that part is just the mixed term here, twice th, I, one more I, and pi. So it is a minus 2 pi th. So the integral from 0 to infinity dt. So this is m plus e 2 pi xh we divide by 2 pi h minus y with minus, but at plus infinity 0, at 0 it is minus 1. So that's a result of integration. And then remember that the denominator is fixed, so we go just along the line with fixed y. H is strictly bigger than the upper bound of y. And we have the same damping exponential factor, so it eats up growing exponential factor coming from there. So g of z goes to I plus of z e 2 pi I cb z goes to 0 when the real part of z goes to minus infinity. And putting all together, now we have proven that g of z is really a bounded function. And so that completes the proof of the Fourier transformation formula. Do you have questions? It was very technical. I'm sorry about that, but integrals are always like this, you know. It's when you don't know how to calculate them. But here we are very lucky. We have managed to calculate the Fourier integral. This is incredible, at least to me. It's very rare situation when we know how to calculate Fourier integral, right? And this is one of these rare cases. Okay, so let us turn back now to pentagon identity, 5-term operator identity. So remarks on 5-term operator identity on phi b of x. Okay, so far not on phi, just the identity of the form p hat phi of q hat equal phi of q hat phi of p hat plus q hat phi of p hat. And we have shown that this identity is satisfied up to common multiplicative factor by Fourier function, phi b of x. And now we are going to first of all prove that the multiplicative factor is really 1, something which we haven't proven yet, right? And we'll see that this equation now gives a nice integral identity for the function phi b itself. So we had was it a theorem, the integral version of that? So this is equivalent to phi tilde of s phi tilde of t e 2 pi I s t equal integral over r phi tilde of t minus u phi tilde of u phi tilde of s minus u e pi I u squared du. You remember this equation, which was called integral relation, right? I think it's theorem 11.1 or something. Lemma F2, okay. 11.2, thank you. Lemma 11.2, right? So we have this equivalent version of this equation, which should be thought as a distributional identity, in the sense of tempered distributions. And yes, so it's a good moment to stop here, and we will work out a little bit further this identity after the break. Yeah, so we have this 5-term integral identity, and let us do first the following thing. So we multiply integral relation by e2 and integrate over t. In the left-hand side, what we will have? We will multiply this by extra exponential factor. So the ultimate exponential factor will be 2 pi I t times s plus x. And when we integrate over t, this will be just the inverse Fourier transform. So we will get back to phi. So we will have phi tilde of s, which is t independent, so it behaves like a constant. But the rest will give us phi of x plus s. Right? That's the result of this operation for the left-hand side. And let us see what we'll get for the right-hand side. So now integral will be double. Phi tilde. And now I'm going, because we are integrating over t and along the real line. So we can translate t variable. So I exchange first the double integral. And then first integrate over t. But since here the argument is t minus u, I will shift the integration variable by u to make the argument of this phi tilde just t. Right? So I write t of t. And I put next to it this exponential. But now t is translated. So instead of t, I will write t plus u times x. And the rest is stays intact. Phi tilde of u, phi tilde of s minus u, e pi I u squared du, dt and du, dt and du. But now we again recognize the Fourier transform of phi tilde. So the integration over t is removed by changing this phi tilde to phi. So again integral is over r now, the u integral only, which remains. And here, instead of this phi, we get the phi of the multiplication coefficients of the integration variable t, which is x. Right? And the rest stays 2 pi I ux, phi tilde of u, phi tilde of s minus u, e pi I u squared du. And now we can give phi of x is a function which takes its values on the unit complex circle. So we can divide by it without any problem. So we get phi tilde of s, phi of x plus s, divided by phi of x. And now I will say something more. Now we divide, right? So this is the left-hand side. Something what remains, this integral. But if you look at this integral, it is a Fourier integral in variable u with a new Fourier image variable x, because x doesn't enter anywhere else, right? So we take a inverse Fourier transform of this equality. So taking the inverse Fourier transform form in x, right? We obtain, so what we will have here, integral over r. E, here we have plus, so the inverse will be minus 2 pi I ux. But this time we integrate over x. And then we rewrite the remaining part of in the right-hand side without u integration. So phi tilde of u, phi tilde of s minus u, e pi I u squared. So you see, we removed the identity is still 5 term because there are 5 phi's. But there are only 3 phi's which carry tilde. And 2 phi's don't carry tilde anymore, so this is explicit. So even if, up to now, so the argument is valid for any function satisfying this 5-term operator identity. But from that moment, we now assume that phi is given by Faddeev's function. And because for Faddeev function, we know what is phi tilde by the previous calculation. So I remind you that this is for any S and U on the real line. So this is still distributional integral identity. So now we take phi of x to be lambda Faddeev's phi b of x. Why lambda? Because I remind you that we proved the 5-term identity only up to multiplicative scalar constant, because we proved it by conjugating operators by left-hand side and right-hand sides of the equation. So this fixed the identity only up to multiplicative constant. But we remarked that this constant eventually is equal to 1, but now we are going to see why it is 1, right? So, but I keep it for a while. And then we substitute. So let us write out phi tilde of x now becomes a lambda zeta 0 e minus pi I x squared phi b of CB minus x, right? That's a formula if we use the complex variable and z, which is in the domain of analyticity of the function. But now we are in the distributional world, and x is a real variable. And of course, now we have a problem for real x. When x equals 0, we hit the pole. But in distributional world, it's a normal thing. The only thing we have to care about how we treat the pole, right? And since this distribution should be thought as a limit of the analytic function from the domain of its analyticity, then we have to put here minus I epsilon or I 0, which means that we should attribute to x a little positive imaginary part. Now we are in the analytic function. And then, so this imaginary part is arbitrarily small. You remember this distributional formula 1x plus I0. Right? This is minus pi I delta function of x plus a principal part of 1 over the x. So the prescription minus I0 is like here, right? In this famous Plimel-Sahotsky or something like this, for the distributional equality. And we put this minus I0 in the same sense as we put it here. Okay? So because it tells us how we treat the singularity at x equals 0, likewise here. Okay, so that's a Fourier transformation in the distributional sense. Okay, now we substitute all that. So we get lambda zeta 0 integral phi b of x plus s. Okay, so let me first. Sorry. Yeah, it's okay. Lambda zeta 0 E minus pi I phi of S, so minus S squared phi B of CB minus S minus I0. That's for that term. Now I write the integral fraction phi B of x plus S divided by phi B x just x E minus 2 pi I U x dx equal. Now we have a product of two functions, and this pi I U square cancels the corresponding exponential from the first phi tilde, because it carries similar exponential with a negative sign. So we have a lambda zeta 0 squared E. I write only one exponential coming from the second phi tilde, minus pi I S minus U squared. And the product of two phi B functions, phi B of CB minus U minus I0. So there is no enough space, minus S plus U minus I0. Okay, that we get this identity. We can simplify a little bit by dividing. And now we know that this function does not vanish, right? That does not vanish. It approaches close to the pole, but it doesn't approach any zero of phi. So we can safely divide by this part. And but the pole in the denominator becomes a 0. So we can remove this I epsilon in the denominator. So this is equivalent. This is equivalent to just pure integral over R, Fourier integral of that kind, divided by phi B of x, E minus 2 pi I ux dx equal lambda zeta 0 E minus pi I S minus U squared plus pi I S squared phi B. So CB minus I0. So the same arguments, right? So I will not write them explicitly, but I'm going to do something else. So I'm going to simplify this. If we expand, then S squared goes away, because it is with opposite sign. There will be mixed term. But mixed term we can remove also by transforming the integral a little bit differently. So let me write this as a by shifting x by minus s. Phi b of x divided by phi b of x minus s E minus 2 pi I U x minus s. And now look what happens. So here we get dx. Here we get the term which mixes u and s, right, with plus sign, 2 pi I ux. And the same mixed term shows up in the right-hand side. So we can divide by this mixed term, and we will simplify simultaneously the right-hand side. So this altogether, this is the equivalent to final identity, which I'm going to write explicitly, phi b of x divided by phi b of x minus s E minus 2 pi I u x dx is equal lambda zeta 0. And now after simplification, the only thing which remains is minus pi I u squared. E minus pi I u squared, and the fraction of three phi functions, phi b of CB. Okay, so let me write it once more. Minus u minus I0 phi b of CB minus S plus u minus I0, and divided by phi b of this phi b CB minus X. And we don't put any I0 because the pole in the denominator is 0, so it is not problematic. So that's a formula which I call integral Ramanujan formula, IRF, integral Ramanujan. Phi b CB minus, yes, thank you, of course. Integral Ramanujan formula. Why Ramanujan formula? So just for you, psi 1 1 Ramanujan summation formula. If we look at this, for example, you Google it, psi 1 1 Ramanujan summation formula, you will see something like A semicolon Q n B semicolon Q n z power n in the integers equal something explicit. This is called psi 1 1 Ramanujan summation formula. And so if you look at least to the left-hand side, so you replace quantum, these are quantum products by this phi d function, then summation is replaced by Fourier integral, and you get here something known. Likewise in the Ramanujan summation formula. So this is why this is the reason why I call it the integral Ramanujan formula. Okay, and this is a very nice formula because look, we take a fraction of two phi d functions, and we still are able to calculate its Fourier transform. Right? It's still a very nice fact, but even more. We know that when we send S to plus infinity, if we shift the contour a little bit into complex domain to make this absolutely convergent, then the limit at when S goes to plus infinity allows to replace this phi by 1, right? And then this Fourier integral becomes a Fourier integral for phi itself. And that's, but we know already that this Fourier integral, how to calculate. But now let us take this limit on the right-hand side. Now S goes to plus infinity. This goes away, becomes 1. This becomes 1. And we recover the Fourier transformation formula we have just proved, right, in the first half. But the only difference that the zeta 0 is replaced by lambda zeta 0. But what we know that Fourier integral cannot admit two different constants. So the only way to make two formulas agree is to put lambda equal 1. So that proves that the pentagon 5-term identity is satisfied without any constant for the phi d function. That finishes the proof of that theorem. Okay, so the limit S goes to plus infinity allows to conclude that lambda equals 1. So you see how so indirectly we extract information. So because we don't know how to calculate the integrals, that's the reason. Yeah, okay, now we turn to TQ of T, finally. So I think that practically we finished this technical part. And now everything is ready to go back to topology. So back to topology, or quantum topology. So what we are going to do is we are going to study the tetrahedral weights of Teichmüller TQ of T. So the idea is to take the integral kernel of W operator, take the integral kernel as a tetrahedral weight. So I write it like x1, x3, w hat, x0, x2. Okay, so that's the integral kernel. It's a distributional quantity. But we have 4 real variables corresponding to this matrix, the vectors, basis, generalized basis vectors in the Hilbert space. And how we are going to interpret it is the following. So we draw a tetrahedron, and we order the vertices by integers from 0 up to 3, 1, 2, 0, 1, 2, 3. Okay, so we put orientations on the edges like this. So from a smaller index to big index, we put an arrow, and the meaning of these integers also they count the number of incoming arrows at the vertex. For example, at this vertex there is no incoming arrow, so we have a 0 here. Here we have just one incoming arrow. So this is why we have 1. Here we have 2 incoming arrows. We have 2 and 3 incoming arrows. Okay, so that's a very nice enumeration, right? And which gives the preference for enumerating from 0, not to 1, not from 1. And now the way I put here these indices correspond to faces. So each face is opposite to a unique vertex. So x3 will be put to the face which is opposite to 3. So in this face, I put a variable x3. In this face, I put the variable x2. And in this face, I put the variable x1. And finally, the outer region is opposite to 0, so x0 is on the outer region. So that's a way we think of now of the integral kernel of the operator W. And now, we should be able to explain why we do so, right? So what is the reason that we associate a tetrahedral weight this way to that integral kernel? And the reason is a 5-term identity. So now the identity, the operator identity W12 hat to 3 equal W23 W13 W12 is interpreted as a 2-3 Pachner move in 3D triangulations. So let me draw the picture. So we put and then the enumeration is not arbitrary. So I start. I enumerated like this. I start 0 here, 1. No, 1 here, 2, 3, 4. Okay, so we can put now the arrows. Again, these numbers just count the number of incoming arrows. Okay, so that's left-hand side, and I redraw the same picture. Same picture. So 0, 1, 2, 3, 4. But this time I add one more internal edge, which sits like this. So here you should see 3 tetrahedra, which share one common edge given by edge 1, 3, which is vertical, and inside this 3 ball. This is a 3 ball, right? So a ball obtained by gluing 2 tetrahedra along one common face. And in this 3 ball, you think it is a wooden ball, right? We cut out from a piece of wood. And then, in the left-hand side, if we cut it along the horizontal triangle, 0, 4, 2, this ball splits to 2 wooden tetrahedra. But now let us not do that, but instead we cut it along 3 triangular faces by cutting along this triangle 1, 4, 3, 1, 2, 3, and 0, 1, 3. And then these 3 triangles meet at this edge, and then the wooden piece splits into 3 tetrahedra, right? So that's the meaning of this 2-3 Pachner move. And but now we put the extra orientations, and so the claim is that this corresponds to the integral identity obtained by calculating the integral kernel of this operator identity. So let us do that. So I put x, y, z, w, 1, 2, w, 2, 3, hat, u, v, w, right? So that's what we are going now to calculate, the integral kernel. And now I insert here decomposition of unity. Okay, let me try to do it a little bit differently. So x, y, w. So w1 to x on y and x and y, but does not touch z, right? Because 1, 2, x only in the first two components. So I put here x, y, x, y. Do we have more letters? X, Y, Z, U, V, W, R, S, T. R, S, T. R, S. Right? R, S. And here we put R, S, Z applied to W, 2, 3. But it doesn't make sense to keep this sub-indices when we specify explicitly the operation of W. Rs, Z, and U, V, W, dr, ds, right? The double integral. No, sorry. This is triple still, so we have to keep here this indices to 3, which means that we have a delta function in R and U, because this doesn't touch this vector. So we can remove integration over R by replacing R by U. Sorry for that. And I erase the first. And now we can remove to 3. Here is a formula and a simple integral. And now we can, that's it. That's it. And now let us do the same for the right-hand side. W23, W13, W12, UVW. And again, so we have, let us do this. So it does not touch X. So it is Y, Z, W, RS. RS, and here I put X, RS, W13, W12 hat, UVW. dr, ds. So far, double integral. And now here we have 1, 3. So it does not touch R here. So we have integral yz w everywhere hats w hat rs, and now we don't touch R, so it yeah, x s w. Okay, we have T. And are there any more letters? Okay, A. And yes. So what remains here? Instead of X, we put T, right? T. Instead of R, just passes through, and A. A, W hat, 1, 2, U, V, W. So triple integral, dr, ds, d, quadruple integral, rs, dt, dA. Okay, so quadruple. But again, for the same reason as before, this kernel produces one delta function in subspace 3, right? Because it doesn't act, it acts trivially in 3. So A and W this is a delta function. So we can erase the integration over A and replace A by W and remove this A and this W and remove 1 to here. So that's the final form. Now integral is triple. And now I claim that this integral identity exactly corresponds to this triangulation with colorings. And now we can try to identify the colorings. For example, here we have a simple integration, right, in S. And we have only one interior face here, 0, 0, 2, 4. So I claim that this S integration corresponds so is identified with the integration with the face variable living in face 0 to 4. Okay, so let us attribute S becomes, say, x 0 to 4. Okay, the coloring variable. And let us see if it is true as concerns the W. For example, upper tetrahedron. So the indices for upper tetrahedron is 0, 1, 2, 4, right? And then it is opposite to 1. To 1, it should be leftmost variable for one of these W functions. And indeed, you see, this is the upper tetrahedron. Upper tetrahedron. Because the S is opposite to vertex 1, and it is the leftmost, you see, as here. And this is a lower tetrahedron. And the S is the rightmost variable. And let us see. Here we have an enumeration 0, 2, 3, 4. So 3 is a second last vertex, vertex which corresponds to 2 here. And you see that S exactly stays in the right place. And you can go on. You can check in this way that the correspondence is absolutely precise in that sense. Okay, I will not discuss it anymore because now you can see that you have triple integral. You have 3 interior faces here. And just by looking at this picture, you can identify face by face which variable corresponds to which variable in both sides. Okay, so I leave it here. And we have 5 more minutes to calculate this integral kernel. That's what I want to do now. Calculation of W. Let me put just x st xy. Okay, so just to avoid the indexation. Remember what was the formula? It was a phi of q1 minus q2 plus p2 e minus 2 pi I p1 q2 xy. Right, that's the formula. Now q2 hits its eigenvector. So q2 can be replaced by y, right? Because q is a diagonal in the basis. So we write it replaced by y. But now this okay. So let me calculate the. So it is a xy 2 pi I p1 y, right? So because we replace it by y, and this is the Hermitian conjugate of that vector. But pi1 is a differentiation. differentiation. So I can put it 1 y d over dx acting on this vector, Hermitian conjugate. So I pull it back. I'm using the rules of the game, right, which were fixed in the very beginning when we introduced the L2 of R. And now, what is the action of this differential operator? It is a shift of the corresponding argument. So this is the x plus y, comma y, Hermitian conjugate. And then when we apply Hermitian conjugate, we end up with this. Okay, so all that is equal to that. So let me write st phi of q1 minus q2 plus p2 hat y x plus y. And now we use the Fourier expansion integral phi tilde of t st e 2 pi I t q1 minus q2 plus p2. So I have to separate this. Yx plus y dt. Right? Now it remains to calculate this, this kernel. And for example, q1 already hits its eigenvector. So q1 can be replaced by s already. And the only thing which remains is to calculate the rest. So integral over r phi tilde of t. So e 2 pi I t times s, right, because of q1. And what remains, so then we have a delta function of sy, right? I don't like this. Okay, sorry. I mixed up the order, right? X plus y, y. Sorry. So we should keep the same order. X plus y, y. And so we have a delta of s minus x minus y, right? The first delta function, and the remaining thing is e t e 2 pi I p hat minus q hat applied to y dt. And unfortunately, we don't have time to finish this. So this will be an exercise for you to calculate this matrix. And a very easy exercise, okay? It's just, and the integral over t will be removed. And the Fourier transform we know for phi. So you see the integral kernel is calculated in closed form. And we will next time, it's the last lecture, right? Next time we will discuss this formula, and we will put more geometrical data in it, because up to now it is a distributional formula. And remember that this has a pole, right? We have a prescription for the passing through the pole, and then when we switch in extra geometrical data, the effect will be the regularization of this Fourier transform by a Schwarz class function. Namely, we will be putting the imaginary parts of the corresponding variables. But these imaginary parts will get interpreted in geometrical terms as dihedral angles of ideal tetrahedra in hyperbolic space. Okay, I stop here. And if there are questions, please ask.